Dear students, today we are going to see benzoin condensation. So first we'll see the definition. Two aromatic aldehydes undergoes condensation in the presence of aqueous alcoholic potassium cyanide or sodium cyanide. We are getting alpha hydroxy ketone. So what is benzoin condensation? Two aromatic aldehydes undergoes condensation in the presence of aqueous alcoholic potassium cyanide or sodium cyanide, and we are getting alpha hydroxy ketones. So here addition of one molecule of aldehyde reacts with the carbonyl group of another molecule of aldehyde, and we are getting alpha hydroxy ketones. Now we'll see the reaction for this. So first we have taken one molecule of aromatic aldehyde, that is benzaldehyde, reacts with another molecule of benzaldehyde in the presence of aqueous alcoholic potassium cyanide or sodium cyanide, and we are getting alpha hydroxy ketones, and that can be called as benzoin. Specially can be called as benzoin because so here this is the functional group. So ketone is the functional group. So according to the functional group, the next carbon, no, that is alpha carbon. So alpha carbon is having hydroxy. That's why it is called alpha hydroxy ketone. So what is the reaction? Two molecules of aldehydes, I mean aromatic aldehydes, undergoes condensation in the presence of aqueous alcoholic potassium cyanide or sodium cyanide. We are getting alpha hydroxy ketone, that can be specially called as benzoin. So now we'll see how we are getting that benzoin. So here we have the ketone, no, I mean that carbonyl group. So that would be cleaved, bond between carbon and oxygen, that would be cleaved. That's why. So here we have that carbonyl carbon of next aldehyde. So that comes and attaches with this carbon, and here we have hydrogen, no, that hydrogen is moving here and attaching with the oxygen, and that would be converted to hydroxy group. So we are getting alpha hydroxy ketones, that is called benzoin. So what is benzoin condensation? Two aromatic aldehydes undergoes condensation in the presence of aqueous alcoholic potassium cyanide or sodium cyanide. We are getting alpha hydroxy ketone. Otherwise, it can be called as benzoin. So if you are using two molecules of benzaldehyde, we are getting the product as benzoin. Now we'll see the mechanism for this. So first step is formation of an anion. So now we are taking one molecule of benzaldehyde, and that is treated with a Cn minus, that is obtained from potassium cyanide or sodium cyanide. We are getting cyanide ion. So now we are taking cyanide ion, and that would be added with one molecule of benzaldehyde. So by that addition, what happens? Here it is actually it is a nucleophile. So it has to bind with the electrophilic carbon. So this Cn comes and attaches with the carbonyl carbon of the first aldehyde. That's why. So here, because of that attachment, the valency of carbon would be changed. No, that's why to satisfy that valency, here the double bond would be cleaved, and that would be converted to single bond. So bond becomes negative charge. So that's why we are getting this product. So Cn would be attached with this carbon, and double bond would be converted to single bond. So bond becomes a negative charge. So O is getting negative charge. That can be called as anion or an alkoxide ion. Next step is proton transfer, that is rapid proton transfer. Now we are taking that alkoxide ion, that is anion, it undergoes rapid proton transfer. So on rapid proton transfer, what happens? The hydrogen present here, no, that is moving and attaching with the oxygen. So that's why here we have negative charge, no, that is shifted to the carbon. So negative charge is coming to the carbon, and we are getting the product called as carbanion. Otherwise we can tell it as a nucleophile. So what happens in first step? Here we have cyanide ion, no, that is obtained from potassium cyanide or sodium cyanide, that comes and attaches with the carbonyl carbon. That's why the double bond would be converted to single bond. So the bond would be converted to, so bond becomes a negative charge. So that's why oxygen is getting negative charge, and we are getting anion. Now there may be rapid proton transfer. This proton is, I mean proton attached with the carbon, that is moved to the oxygen. So O converted to OH. That's why this negative charge will be converted to this one, converted to carbon. So C is getting negative charge. That can be called as a carbanion, and that is acting as a nucleophile. Here this carbon is getting greater stability because of the presence of this cyanide. Now we'll see the third step, that is the reaction of carbanion with another aldehyde molecule. So now we have taken that carbanion that is treated with another molecule of aldehyde. So here this is acting as an electrophile. So by that addition what happens, here we have double bond no, between carbon and oxygen. So that would be cleaved and bond becomes negative charge. So to satisfy the valency of this carbon, that has to unite with the carbon that is having negative charge. So we are getting the product as one more anion. So here this carbon is connected with this carbon, that's why the bond will be converted, double bond will be converted to single bond. So oxygen is getting negative charge. So here we are getting an anion, and that anion otherwise can be called as hydroxy alkoxide. So here this carbanion attacks the carbonyl group of another aldehyde, and we are getting anion or hydroxy alkoxide. So next step is again rapid proton transfer. So here we have taken the anion, that is the hydroxy alkoxide. So it undergoes rapid proton transfer, that is the H attached with oxygen, no? So that H is coming here, that's why the negative charge is moved to this oxygen. So here we are getting one more anion, and that can be called as again one more hydroxy alkoxide. Now we'll see the last step, that is removal of cyanide ion. So now we have taken that hydroxy alkoxide, from that alkoxide here that cyanide ion, no? So cyanide, no, that will be removed as cyanide ion. So on the removal what happens, this bond here it is actually connected to one bond, no, that bond is shifted here, that's why that would be converted to double bond O. So negative charge becomes bond and we are getting double bond O. So that is benzoin, otherwise we can tell it as alpha hydroxy ketones. So here how we are getting that benzoin, through the formation of, through the dissociation of the leaving group. So which is the leaving group here, that is CN minus. So because of the dissociation of the leaving group, here we are getting the product alpha hydroxy ketone, so otherwise called as benzoin. So if you are using a chiral catalyst, we are using chiral catalyst means we can get benzoin with a significant stereo selectivity. So we can get a significant enantiomer in excess. Now we'll see the role of a cyanide here. So first one, it is acting as a nucleophile because it is an electron withdrawing group, so it permits the loss of aldehyde proton. And second one, it stabilizes the carbanion and acting as a good leaving group. Now we'll see the applications of this benzoin. So first one is, so now we have taken benzoin that undergoes oxidation in the presence of copper sulfate, pyridine and water. So on oxidation what happens, here we have secondary alcohol, no? So this is secondary alcohol. So secondary alcohol on oxidation, usually we have to get ketone. So instead of CHOH, here we are getting, so here we are getting CO, that can be called as benzoyl. So benzoin on oxidation by means of copper sulfate and pyridine, we are getting benzyl. So secondary alcohol is converted into ketone. Now second one is, so we have taken benzoin that undergoes reduction in the presence of tin and HCl. So what is the catalyst used here, that is tin and HCl. So on reduction what happens, here we have oxygen. What is reduction? Addition of hydrogen or removal of oxygen. So this oxygen is removed, that's why we are getting CH2 in that place. CHOH would be converted to CH2, that is by the removal of this oxygen, that can be called as desoxybenzoin because only one oxygen is removed, that's why desoxybenzoin. Now we see the third one. Again we have taken benzoin that undergoes reduction. So for the earlier reduction we are using tin and HCl, whereas here we are using sodium, mercury and ethyl alcohol. So by that addition what happens, here we have CO, no, so the double bond would be broken. On either side of the double bond, we are putting 2H. So with the carbon 1 hydrogen, with the oxygen 1 hydrogen. So CHOH. That can be called as hydrobenzoin. So what is the product you are getting? Hydrobenzoin. If you are using tin and HCl, we are getting desoxybenzoin. If you are using sodium, mercury and ethyl alcohol, and that would be reduced, we are getting hydrobenzoin. Then next one, again one more reduction, but here reduction by means of Clemmensen reduction, by means of Clemmensen reaction, that is amalgamated zinc with HCl. So Clemmensen reduction, here what happens, here we have actually this oxygen would be removed, and instead of that bond is coming here. So here we have the bond between carbon and oxygen, no? So oxygen is removed, that's why bond is coming here between that two carbons. So here one H, here one H. What we are getting? We are getting stilbene. So if you are using tin and HCl, the product is desoxybenzoin. If you are using sodium, mercury and ethyl alcohol, the product is hydrobenzoin. If it is a Clemmensen reduction by means of amalgamated zinc and HCl, we are getting stilbene as the product. And one more reduction. So benzoin undergoes reduction in the presence of Raney nickel. So here on reduction what happens? Oxygen. So here this oxygen would be removed, and here this also would be removed. So instead of this oxygen we are adding two hydrogens. So C6H5, CH2, CH2, C6H5. So that can be called as dibenzyl. So here we have seen four reductions. One by using tin and HCl, second by using sodium, mercury and ethyl alcohol, third by using Clemmensen reduction, and fourth by using Raney nickel. So that's all about the applications of benzoin condensation. Now we are going to see the salient features of this benzoin condensation. Already we have seen this is only for aromatic aldehydes and glyoxyls. So only aromatic aldehydes and glyoxyl can undergo this condensation. Then here there may be addition of one molecule of aldehyde to the carbonyl group of another molecule of aldehyde. Some aldehydes undergo self-condensation and they are acting as donors and acceptors. I mean donor and acceptor. Main example for this is benzaldehyde. But some aldehyde can act as only a donor, not an acceptor. So they can't be self-condensed. Example is dimethyl amino benzaldehyde. If the same aldehyde can act as a donor and acceptor, it can be self-condensed, but it can act only as a donor, not an acceptor, means it cannot be self-condensed. Example is dimethyl amino benzaldehyde. So it can condense only with benzaldehyde. Certain thiazolium ions can also act as a catalyst for this reaction. If you are using only aliphatic aldehyde, we can get the product as acyl ions. If you are using mixture of aliphatic aldehyde and aromatic aldehyde, the product is alpha hydroxy ketones. That's all about benzoin condensation. Thank you.